All right. Hello, everyone. I watch a lot of these videos online, so it feels great to be here in person. What we're going to talk about is how we use serverless architecture at Lead to solve the problem of recon and also build a platform for other fintechs to build a card program on top of us. A little bit more about me. I'm an engineer at Lead, leading the financial platform team that spans lending, credit cards, and debit cards. Before Lead, I'd worked at Bolt, a checkout company, and before that, I worked at VMware. On a personal note, I love playing football, or soccer as it's called here. So if anyone has EPL or Champions League predictions, happy to talk about it in the end. What Lead does is we build primitives and APIs for fintechs to build their fintech products on top of us. We provide APIs like the payment ones, ACH, wire, internal bank transfers, check, FedNow, and things like that. And also offer primitives for fintechs to build lending or card products. What this talk will mainly go over, let's go over it in 3 parts. The first one is what sort of recon is sort of needed to support a card program. Recon is a very overbloated word, so we'll dig into what it means, especially in the context of card. After that, we'll dive into the architecture of how we use different serverless tools and why we use those. And then we have built this and have launched it for about more than a year, and we've ran into a lot of challenges. So we'll be going over that and some lessons we learned and how you can scale these serverless tools. Before I dive into what the recon problem is, first let's just get a card primer, especially for the bin sponsor model. There are multiple models, but I'm mainly focused on the bin sponsor model, where the issuing bank is the bin sponsor, and the fintech is the program manager. The fintech manages the relationship with the end customers. But on a high level, how this flow works is, let's say there's a swipe at a merchant. This is for your favorite ice cream, and then this goes to the merchant's POS device, is where the swipe usually happens, a Square terminal, a Clover terminal. Then this is routed to the acquiring processor, where the acquiring processor uses card data as well as transaction data. It forms an ISO 8583 message and then forwards it to the network. The network then looks at the first 6 digits of the card number. This is called as the bank identification number. The network will have a routing table, and it will know where to route this specific message. So in this case, it will route it to the issuing processor, where the issuing processor will run its fraud rules and then either reject or approve the transaction. At this point, let's say it approves it, all of this goes back to the merchant, and you get your favorite cup of ice cream. Some examples in this are, merchant can be any of your favorite ice cream coffee shops. The POS device is Square or Clover. There's a lot of innovation over here where some fintechs have built both the POS device and the acquiring processor. The common acquiring processors are TabberPay, WorldPay. For the network, we work with Visa, MasterCard as primary networks. And the secondary networks over here are Maestro, Pulse. On the issuing process side also, there's a lot of innovation going around. Some popular names over here are Galileo, Lithic, Marqeta being one of them. An important thing to note over here is that money still hasn't moved yet. It's only the auth which has happened. And after the auth happens, the merchant, once the goods have been delivered, the merchant clears these transactions. And this is where the network sort of sends a drawdown request to the issuing bank. Visa's timeline for this is they send a drawdown at around 8 a.m. Mountain time. And then the issuing bank sort of has to fulfill this request and send the money to the network. This is over the wire protocol. And after this, the network then sends money to the acquiring bank, and this is when the merchant gets the money. So until here, so this is how money moved. But what Visa also does is, Visa or MasterCard both, they send in some report files to all the participants in the workflow. VSS sends in a VSS 115 file. Actually, it sends in many VSS files. One of the main ones which we consume is the VSS11 file. It's a summary file which will include the transaction data, what was the aggregate refund, dispute, fees, interchange, and all of it. Similarly, MasterCard also sends in their T112 file, T460 file, as well as the T140 file. So after going over this, let's step into what sort of validations an issuing bank sort of does. But before that, let's cover how we decided to model the fintechs and fintech structures into our objects. So some of these are entity, which is your end user for the fintech, the account, which is a container to hold metadata, card, which is an instrument to move money, balance, which is a value holding object, and transaction is any action or operation which happens on a balance object, which changes the underlying value. How all these objects relate with each other is important, and therefore I'll go over this through an example. So let's say I'm a Wise or a Revolut customer. So that's me, the entity. I will have an account with Wise or Revolut in this case, and this is where I will assign my co-signed users or authorized users. If there's any underwriting data, it will be on this object. And then there are balance objects, so I can have a USD balance, I can have a Euro balance, INR balance, and when a transaction occurs on a card, this is where the balance object's value changes. And for a fintech, they have to provide us all this data. I'm limiting my talk to only debit cards, so if someone wants to talk about lending or credit cards, I'm happy to sync later on. The main sort of recons which we do over here, there are many of them, but some to highlight over here would be, we look at yesterday's balance plus today's activity, which should be equal to today's balance. We mainly do this to ensure the fintech is sending us all the balances and also all the transactions which they've seen. The second which we do is we recon the balance file with the underlying FBO. This is to ensure that since both the transaction and the balance files are created by the fintech, we need to ensure that these values aggregate to an external entity, which is the FBO, where the money actually lives. We also then recon all the card transactions with the network files. Apart from this, we also have some compliance validations which take place on the entity object, the account object, and the card object. For entity, it's mainly KYC data. For account, it's what sort of co-signed users are there or authorized users are there. If there's underwriting, have they provided us the underwriting documents? And for card, whether it's expired or not, and things like that. We also use the same data for Interfi, which is a downstream consumer, which helps us with our capital ratios, and also for fintechs to get FDIC insurance of more than 250K. So once we decided on the problem statement, we were debating should we create these interfaces to be files or APIs. There were a lot of debates over here. We already had endpoints for ACH, wire, internal transfer, and also entity. But when we took a deeper understanding of the problem, we realized that we did not care about transactions and balances as they were changing. We only cared about the end-of-day balances and the end-of-day transactions, because we can sort of do a recon at that point. And this is where we decided to move with files. We also talked to a lot of the fintech partners over here, and we realized that they already had existing integrations with banks, and if they wanted to have a different bank partner, for them to create APIs for just our use case did not make sense. And that's why we ended up with files for transactions and balances. For all the other objects, we were sort of expecting it to be API objects. So to recap, there were two main requirements we wanted to build off. One is files will be dropped at any point, and multiple files. And it could be dropped by multiple players over here. It could be dropped by the issuing processor or the fintech. And we also needed to ensure that recon happens between multiple entities over here, the network, the program, and the bank core. So that was it for context, but once we started building the entire architecture, we realized there were certain principles we wanted to adhere to. One was fast time to market. Since we are a startup, we wanted to build, get feedback, and iterate on it. And therefore, we wanted to optimize on it. We wanted it to be cost-effective, highly available, and reliable. We realized that latency is not is important, but not top priority because it's an asynchronous workflow. And we are not there in the swipe flow, and therefore we can take our time. And therefore we decided to focus on business logic and not infra. Serverless also helped us scale automatically, and therefore we decided to dive deeper into serverless. So on a high level, this is how the architecture looks like. So this is broken down into multiple flows, but for the network flow, what happens is the issuing processor drops in the file. This is, for Visa, it is the VSS115 file. For MasterCard, it's the T112, T460, and T140. And there are multiple other reports also which we consume, but for simplicity, I'm just mentioning these ones. Once they drop it into the SFTP folder, we sync it to S3. And from there, there's an event bridge rule which is listening to this. The event bridge rule then kicks it off, sends it to the issuing queue. Over there, there's a Lambda which is polling the issuing queue and consuming these events. The Lambda checks that the file was in the network settlement directory, and therefore it knows to kick off the network settlement workflow. What happens over here is we convert the Visa or MasterCard files into our format and then store it into the network settlement table. Over here, the main fields we care about are the aggregate amount of transactions, the refund amount, dispute, and interchange. After this, we also do network settlement accounting. What this means is for debit card programs, there is an existing FBO where we pull money from and then move it into a settlement DD account. This is the account from which we send money to Visa or MasterCard. For credit, we originate this amount from a loan GL and then send it to Visa, MasterCard. So that was the network flow, but what happens on the fintech side is they drop in files into the SFTP folder, and very similar to the previous flow, this moves from the SFTP folder to the S3 bucket, and then to Amazon Event Bridge, where we have certain rules, and moves it to the queue, and then the initiator sees that this was a fintech file, and it starts a validate step function. This is where step function is an orchestration layer, and this is where we validate the schemas align. We load a lot of this into our DynamoDB stores, and then we run a couple of the recons, which I mentioned previously. So this is a combination of both of the previous slides, but I've added two pieces over here. To highlight those two pieces, this is the first one, which is we compare the transaction which the fintech centers along with what the network centers. This is to ensure that we are seeing all transactions which happen through the network. Settlement is a very difficult thing to nail, and therefore we have certain thresholds built in over here. Similarly, we also check the balance object with the core FBO object. So that was it on the architecture side, but why did we decide to choose certain tools? We knew that files would be dropped and we cared about events, and therefore we wanted to some sort of a service which will listen to these events and route it to the right integration. Event Bridge lets you capture these events, and it has a lot of pattern matching rules you can play with. With this, we also got fine-grained control and filtering logic to route it to the right service. In the previous example you saw where we were routing it to SQS. The main reason we did that was Event Bridge is just a fire and forget. It doesn't store it. But SQS is where we sort of store this event. And let's say the consumer is down for some reason. So let's say the Lambda is down for some reason. SQS will hold on to this and then put it into a DL queue after 3 tries. This is where we are sure that we get durable and at least once delivery. This also really helped us to decouple our event producers and consumers. The next is the compute layer. This is where we used Lambdas and ECS Tasks. ECS Tasks, very similar to ECS, is a container, but ECS Tasks are a different variation of ECS, wherein Fargate sort of runs these ECS containers, and all of this is self-managed for you. This is where most of our business logic was stored. There was next to nothing infra maintenance needed from us because AWS was managing all of this. We wrote it in such a way that all of these units of work were composable. What really helped us is since these were all small units of work, we could use it across different use cases. So we use it across credit, debit, and lending. Therefore, we were able to scale from a debit program to a credit program to a lending program fairly quickly. Lambdas over here were used for lightweight tasks, especially validation, matching, and things which we were guaranteed were less than 15 minutes. For ECS, for tasks which were not guaranteed to be done in 15 minutes, we use ECS Tasks over there. There'll be a framework in the end wherein I talk about the key differences of when to choose one versus the other. So that was it from the business logic side, but we need an orchestration layer for all of these units of work. This is where step functions come in. Step functions give you complex branching logic. You can also run one unit of work parallelly or across a map. Step functions run for 1 year. I have no idea why someone would use it for that long, but our use case was for a day, wherein a step function started, it ran, and before making our accounting entries, we sent an email to the accounting team. This was mainly only for the first 2 weeks of a program to ensure we are moving money in the right direction. The accounting team saw this email and then approved or rejected this email. So the step function was paused until that point, and once it got an approval, at that point it moved to the next step and made these accounting entries. Step functions also helped us with visual debugging, retries, and timeouts. An interesting thing over here is, let's say within your step function, a step fails, you can resume it from that point. So if, let's say, the previous steps weren't idempotent, you don't have to get into that complexity, and you can resume it from where it failed. These are some diagrams for step functions. So on the leftmost side is one step function where we map over different networks. So we have the same step function, but this maps over Visa, MasterCard, and the other secondary networks. The second image is where I show there's an ECS task, there's a Lambda, there's some branching logic, and try-catch blocks. You can listen, so whenever there are errors happening, you can sort of catch those and then alert your tool. And on the right-hand side, you can see how it makes debugging very simple. You can click on one of these tasks, look at what the input was, what the output was, and also logs. So after a run, it makes debugging very easy. And we need something for storage. This is where DynamoDB comes in. DynamoDB was fully managed. Auto-scaling was also part of it. It was schema-less, highly available. What DynamoDB does is for every item, it makes a replica in 3 AZs. And if you want it to be replicated across different regions, DynamoDB also gives you an option for global tables. It also had simple query patterns, or actually so we thought. I'll get to that later on. It was highly scalable, and we used DynamoDB streams, which was really helpful, which sent a change data capture of all the items when they were coming in. We forwarded this to an ETL, we forwarded it to Snowflake, where a lot of analysis and reporting was done. This data was then piped to our fraud and AML vendors, wherein the compliance team was monitoring. Apart from this, we were also doing accounting on our banking core. This is the ledger of record. So that was it from the architecture side of things. But while building all of this, there were a lot of challenges we faced, and this is just that and how we adapted through all of that in 3 main sections. First, I'll go over the bottlenecks, then some strategies to get most out of these serverless tools, and then in the end, lessons we learned. So the 3 main bottlenecks were Lambda started timing out at 15 minutes. The second one was DynamoDB writes were throttled. And the last one was CSV file size being greater than 1 GB. So when this happened for the first time, we didn't have a lot of alerts. And therefore, Honeycomb came to our rescue. It sort of showed us how our spans looked and how they were separated out. So over here, you can see the blue line is writes to one table, and the green line is the write to another table. So a quick win for us in the first phase was just split this out into different Lambdas. Because both were serial, we can also have different Go routines calling this in parallel. And therefore, we then scanned all of our Lambdas to see where we could split into multiple Lambdas. We got a lot of benefits over there, and we could move quickly. That's when we started investing in ECS Tasks. And therefore, this slide sort of shows the key differences between them and when you should use them. So the first one is, if you're guaranteed that your task runs in 15 minutes, you should use Lambdas. If you're not guaranteed, ECS tasks sort of help over there. They run for unlimited amount of time. ECS task is just a container, so you write a Docker script which starts it. How Lambdas work is, when Lambdas get a lot of requests, it runs in 2 phases. The first phase is the init phase, and the second is the invoke phase. For init, what it does is it starts a micro VM, loads your code as a zip file, sets up the environment, and then creates an execution context. This is only done once for the life cycle of that Lambda. And then after that, all the calls will only run your handler directly. This is where AWS has sort of optimized this for you. There are other options you have for some languages like Java. So when an anecdote over here is, when we wrote one of our Lambdas using Java first time, it took 8 seconds to serve a request, and we were like, this is not possible. So then we switched to Golang, and we were able to get this down to 100 milliseconds. But then AWS came out with something for Java recently called Snapstart, wherein it saves the entire context, and then when you get the first call, it just boots it up directly. So this is where Lambda makes sense, if you have a lot of bursts of requests or high traffic, while ECS task it starts the same container always, so it takes a lot of time to start. And this is not great for burst use cases. Some couple of minor differences also over here are, the max code package is 50 MB compressed and 250 MB uncompressed. For ECS task, your code size can be up to 4 GB. Lambdas also have a lot of integrations because it came much before ECS tasks. One thing which really helped us over here was we set this up in such a way that moving from a Lambda to an ECS task was very simple. It was as simple as just changing the code from start Lambda to start ECS task. And on the infra side also, it was one line of code. So that was it from the compute side. But on the storage side, we were being throttled by Dynamo. So before I dive into some examples of how to improve that, let's dive down deeper into what Dynamo looks like or how it operates. DynamoDB is just a collection of items, and you need to specify 2 things. One is a partition key and a sort key. Partition key is how Dynamo decides where all your items live, in which node, and it keeps all of those items closer to each other so that when a call is made to the partition key, it can get all of that in one request. And DynamoDB gives you certain indexes wherein you can query your data efficiently. One is an LSI, which is a local secondary index, and second is a global secondary index. The local secondary index lives with your table, and the global secondary index is managed by Dynamo, but it's a different table. So when you're writing to your main table, Dynamo asynchronously writes to this global secondary index or a different table. You can set up different partition keys and sort keys for the GSI, and you can make queries over here. One important call out over here would be the local secondary indexes support strong consistent reads, while global secondary indexes, since it's an asynchronous process, will only support eventual reads. There are 2 modes in which DynamoDB operates over here. One is an on-demand capacity mode and a provision capacity mode. Provision, just like the name says, is you can set your limits, but you have to pay for all of it throughout the duration when you've set these limits. And on-demand is Dynamo will manage this for you, all the scaling for you, and you have to pay as your usage. What it does is, let's say it hits your thresholds, and DynamoDB will 2x its capacity based on the last peak, and therefore it's able to scale automatically. However, there are some partition limits which we cannot get around. These are your 3,000 write capacity units per second and 1,000 write capacity units per second. Therefore, it's very important to choose your partition keys and evenly distribute it across all partitions. The AWS SDK also makes handling, throttling very simple. You can set your max attempts. You can define your own exponential backoff procedure, and this works great. So this is something about DynamoDB querying. So on the left-hand side is what we started with. We went with program ID file date, and the GSI was program ID transaction ID. But as you can see, we load all the files for a given date, and this is where we were throttled on the program ID file date. We thought we can switch to it being a GSI and program ID, transaction ID being the primary key, but there was GSI back pressure, and it was obvious because GSI was also a different table. So if you set a GSI PK to be program ID file date, that table will also run into the same issues. So how we got around that was with partition key sharding, or right sharding, as AWS calls it. What this means is, instead of just program ID file date, you can have program ID file date shard 1 till shard n. This will let you scale pretty well. So first time when we encountered this, our writes for, let's say, 1 million records were about 30 minutes. But with this sharding, we were able to get it down to 5 minutes. And AWS also is known for serving more than 1 million requests per second for Dynamo. So this scales automatically without you worrying about it. How you can pick a shard is, we went with just a random number, but we need to ensure that it was well distributed across all shards. The second is, if you have a use case wherein you want to know which shard your item lives in, you can just have a hashing function based on some properties, and then you can store it in one of those shards. All of this was on the application level. You did not have to do anything else. DynamoDB also gives you certain knobs to play with. This is your pre-warm-up throughput. This is where you can set these settings on Dynamo, and it is useful if, let's say, one of your clients or you yourself are expecting a lot of load for a certain day. Let's say there's a sale event, and you know that there are going to be a lot of writes. You can set this value. DynamoDB on-demand mode will scale it up to this level, and you're able to serve all of these requests without being throttled. It also gives you this option of DynamoDB Accelerator, which is a cache which will help you with your read use cases. There was one more advanced pattern which we used, which was DynamoDB Streams. There are multiple integrations over here. So the first one is you can directly integrate into OpenSearch. So if you have use cases for text-based search or semantic searching, you can directly connect it to OpenSearch. And let's say you wanted to aggregate something, or in the SQL world, there's a concept called a stored procedure calls. If you want to replicate that over here, you can consume these streams in a Lambda, operate on it, and store it back into Dynamo. A neat thing over here is with SQL, all of that is happening on the table, but over here, all of this is happening asynchronous outside of the main table, so your performance is not sacrificed. One other pattern is we can store all of this into an S3 Parquet file and have your SQL queries on Athena. All of these are eventually consistent though. So after building this, we initially started with some startup use cases, but as we started seeing scale, we ran into a lot of issues. And therefore, this is just some learnings out of it. Serverless gave us fast launches and low DevOps cost. Our cost for one account on the issuing side was roughly about $1,000 a month, which is insane. We also had to build external recon systems. This is mainly because we're consuming a lot of these files from the fintech. So us comparing these values to an FPO account, or when a network drawdown comes in, we can check this value against what the network sent. So in this case, let's say Visa sends us $100. We can see, once our parsing is complete, we can compare it against the Visa drawdown to ensure these values match. Having that has helped us catch a lot of our bugs and not lead into something big. Since your compute is broken down into so many functions and across ECS tasks and Lambdas, having libraries for a lot of common patterns really helped us to scale these Lambdas very quickly. Knowing hotspots and setting alerts really helped. This is where I think if we would have done this previously, we would not have to make those quick wins at times, and our clients were blocked at times. Having idempotent workflows also really helped, mainly because the clients send us files. If there is an error in those files, we sort of respond back to them. They fix those and then send it again. Therefore, we run the same workflow again. So having those idempotent workflows gives us confidence that there won't be any side effects out of it. If you're using SQS, using something like a DLQ really helps. because you don't lose out on an event after 3 retries or X amount of retries, whatever you choose to configure. We also had some operational lessons over here. So we had a Slack group with all of these clients wherein whenever errors were happening, we were sending it to them. But we forgot to send, as in we did not prioritize sending successful messages. Because of this, there was a lot of back and forth with the client as to have my files been validated successfully or not. And this is where there was a lot of ops cost. And then once we implemented that, that went down. But our error message was also bad, and that's something we're still improving on. Initially, we were launching one or two clients a month, which was okay on the onboarding side. But now we're at the place wherein we're onboarding 3 to 4 clients a week. And this not only includes the cost to launch a program, but there's also there's some cost with helping them in the initial days until they understand our systems. This is where we should have invested a lot in internal tooling for making onboarding better. There were also times wherein, let's say we want to make an accounting entry, there was an NSF wherein the fintech does not have money in their account. So we had to build certain workflows around it so that the accounting team will go and ask the fintech to send money, and then we can run these workflows again. So those were it from the system design and operational ones. But on the interface side also, we made 2 big mistakes. And this is where the first example which I was giving was as file versus API. We had our accounts and card also as files, but then we realized that these are actually just point-in-time objects. So modeling them as APIs would have made a lot of sense. And transaction balances files still works very well because these are batch-based files. Migrating a file schema from one to the other was very difficult, and therefore you need to be very thoughtful about this. You should treat it as an API. You should treat it as an API, and if there are any backward compatible changes, definitely factor those in. So overall, if there were 3 lessons I would like everyone to take, would be serverless architecture enabled us to iterate quickly, and it reduced our DevOps cost. Building externally observable systems really helped clients self-serve and scale. And the last one is understanding how product use cases translate to interfaces really help, because this is the point where you can sort of build an interface for many clients and not only few clients. With that, I would like to thank all the organizers, sponsors, exhibitors, and every one of you for being here. We have some time, so any questions? Yeah.
Are you concerned about having your entire process be tied to just one cloud, or are you thinking about doing multi-substrate at some point?
So that is a good question, and right now, since we are a startup, we went with AWS. It is not on our roadmap for this year, but that's something we will invest next year. We haven't had a lot of incidences, and a lot of these workflows are asynchronous. So if something happens, AWS is very quick in fixing their stuff. And I would say in the last 1 year, only once something might have happened. Yeah. Yeah.
These are a lot of asynchronous flows, but as you pointed out, making sure that you're resolving, making sure that you sit in some of the calls.
Sorry, can you repeat that?
They're async processes, as you pointed out, but they're highly important async processes.
Yeah.
So you guys have an MPU. I'm not sure if it's Spence Leader or the Missouri thing that you use, but it has to happen no matter what.
Yeah.
How do you ensure that no matter what, that these step function flows actually do execute? What kind of safeguards do you have to absolutely ensure 100% certainty?
Yeah. So we have alerts wherein if something goes wrong, we have alerts into Honeycomb where the on-call engineer is alerted and they sort of step in. But apart from that, step functions let you retry multiple times. Having idempotency in all of these workflows is important because let's say you try the first time, it fails, you can retry again. We use Fiserv as our core. So when making those calls to Fiserv, something can happen and they have their windows wherein something might not work. So we have to retry it again, and this happens through a queue mechanism. We log it into a queue, and it keeps on retrying until it succeeds.
Is there any situation where you might miss the reconciliation window for the day?
There are chances, yes. So there are days wherein we might have missed reconciling it on that given day. But since it's not something which affects the business directly, the next day the program can catch up. And we sort of keep on sending that on their Slack groups, saying that you need to catch up, and the program needs to upload those files. But settlement with Visa keeps on happening no matter what. So those are independent workflows. So the fintech workflow is one independent one. The other one was the network one. The network one, we have to send money to Visa, MasterCard on that day. Yeah. Yeah.
I like what you said about the culture of observability over debugging.
Yeah.
What are some of the lessons you learned in that?
So we use OpenTelemetry over there, which really helps us with auto logging, auto instrumenting all these traces. So we have a lot of these function calls between Lambdas, DynamoDB. So OpenTelemetry handles all that for us. So let's say if we don't add a log, OpenTelemetry will take care of it for some extent. Debugging would be for us to go and add certain logs after something's happened. So that's one part of it. The second is Honeycomb really lets you slice and dice data on different attributes. So the more attributes you add, you can slice and dice data on it and get to your problem very quickly. Yeah.
I've never used that Honeycomb before. Is that where you see your hotel data too, or where do you, is there a dashboard for hotel?
Yes. So Hotel pipes a lot of that data into Honeycomb. They're one of the vendors who are there in today's, yeah, and they're pretty good, yeah. Yes.
You guys ingest all your telemetry, or are you guys doing sampling?
So right now we're ingesting all of it. There is something which Honeycomb provides, is something called as a refinery. And also OpenTelemetry has certain receivers wherein you can filter on some data which you don't want to see. So yeah, it gives you multiple knobs you can play with. On your OpenTelemetry gives you this file called as a collector file where you can configure all of this, and you can say we only care about these specific events happening, or these specific logs, or these traces coming out from this service or that service, yeah. Yeah.
So you mentioned about the lessons learned after you go live with the architecture.
Yeah.
And some of them were throttling and the timeouts, and you switch to ECS, right? So I believe that you have realized when you have a scale of input and when you went back and you went to this solution, right? So you had a learning curve with a time duration and you went to this design. And now when with this design, how long you are doing, like, the forecast for? Is it a year? Or like, what do you think, like, where could be the new improvements comes in a year?
That's a great question. So the question was, after the lessons learned, we could scale till one level, but what next? So with write sharding, we're able to get a lot of writes. So DynamoDB is not a bottleneck right now. But let's say it becomes a bottleneck at some point wherein we start seeing 100 million records. At that point, there are the other patterns wherein you can push these into S3, and S3 will then forward it to Athena, wherein you can do your queries. These will be eventual, consistent reads, but they will still be able to get you some level of confidence. Actually, not some level, full confidence into these queries. And yeah, that is one pattern which we haven't delved into yet, but that's something, once we hit those scale, we'll sort of go in that direction. But with ECS Tasks, you also get unlimited time. So this can run any amount of time. And we don't have any constraint on time because it's a daily batch workflow which keeps on running. So, but on the network side, we need to send money, but we have never seen any issues over there because it's just parsing a file which Visa sends and then moving money. So those workflows are not affected. The other ones will be, but we have certain things which we've already kept in mind and which we might transition to when we hit those scale. Yes?
What are you using for unit and integration tests to work through all these different dependencies?
So a lot of our workflow, the question was what do we use for unit and integration tests? So for integration tests, all of this is baked into our GitHub Actions. Whenever someone merges the code, we run integration tests, which are all written in Node.js. We're just dropping the files into our test environment, simulating the entire end-to-end pipeline, from dropping the files, seeing whether the step functions worked, and whether the accounting entries were made into our core. So we have integration tests per account. We do not want to mix each of these because otherwise all your deployments will be interrelated to each other. and we've got a lot of confidence from just testing your account. And all of these workflows will have integration tests written, wherein once files are dropped, we test it till the end wherein accounting entries are made.
So you only integrate, do integration testing live in AWS?
Yes, yes. And apart from that, all these Lambdas and ECS tasks have a lot of unit tests, and that's how we get a lot of coverage, yes.
Do you have a way of capturing like edge cases that happen in production so you can make those into unit tests or into test cases for?
So whenever an incident happens, we sort of, we have a retro on it, and over there we sort of, we check as to what all, how did we miss out on this error happening in prod, and then we write those unit tests and integration tests. But it's assumed that once a feature goes live, sorry, before a feature goes live, the engineer should write a lot of these integration tests because there's a financial workflow. We need to be confident before launching a client, and that's something baked in when we launch. Yeah. Yes, so that would be this one, or?
There was one that right
Yeah.
Thanks so much. How do you handle retroactivity? So when people reverse payments, which is a pretty common thing that you have to handle, I feel like this flow is somewhat set up for that, but do you have a separate flow for step function for like they reverse payment, they can dispute, chargeback, whatever?
Yeah, so this complexity is not handled on our side, it's on the fintech side. So they send in a file, and they only sent in transactions which have been posted. So let's say if something was refunded, we get that in the Visa file. So it's a new transaction, so it's an append on the log. So the refund would be a new transaction, and we sort of will do that recon very similar to the transaction balance recon. And when Visa is sending us that X amount was in refunds, we compare that that value to what the transaction file has.
I see. So you're just getting the delta of what's changed.
Yes.
A very small amount, and then ultimately it flows into your FBO recon.
Yes. And that's a very complicated topic because settlement sometimes is not a finite thing. And that therefore we build certain thresholds, and there are external manual steps which sort of come in. Once the FBO is off, then what the client is saying the balance is.
Yeah, because the fintech sometimes misses it, for example.
Yeah.
It's like catches it, comes in the master file or like the late settlement file.
Yes, and therefore we have a threshold that it should not go over like X amount of dollars for a program. It's a config-based thing, and it's a risk-based decision we make based on the program. Yes.
Talk about observability and debuggability as the system is running, but do you have to build tooling to help your accounting team to debug stuff more at the domain level, like understand why this transaction is put aside?
Yes, that's a great question. So the question is how the accounting team is able to keep up with all of this and what different workflows we have built for them. So all our data, all the accounting entries, sorry, any financial money movement which we do is on Fiserv, which happens through a call which we made to the Fiserv system. This is where the accounting team also has visibility into these accounting transactions. So one thing we do is when the program goes live, before the program goes live for 2 weeks, when these accounting entries are being made automatically, the accounting team gets an email wherein they have to either approve or reject that email, and based on that, we make those entries into our ledger. Apart from this, let's say there are workflows wherein we are moving money from the client's FBO account or operating account for some reason, and they don't have money over there. So we have given accounting team a tool wherein they can go and talk to the fintech, get money, and then retry all of those workflows. And the third was your observability question. This is where we publish a lot of this data into Snowflake. We have accounting team they can create their own dashboards over there. They have their own dashboards wherein they have set up certain thresholds, and they keep on checking that.
So the line items are like replicated in Snowflake, but the bulk items hit that.
Yes, yes. Cool. Yes.
Maybe this is like just because I'm not super familiar with the serverless architecture. Like, are all of these, you have the ECS containers that you spin up, or like the Lambdas, are these all defined in the same repository, like chained together as kind of like a service layer function, or how do you, share that information between each other? How does it plug into AWS?
So there are two parts over there. One is the infra side. So infra side, AWS gives you CDK code wherein you can write all of this into certain files. CDK has a concept called stack. So you can create stack for different use cases or different infra level logic. So you can create a Lambda stack, an ECS stack, and all sort of have dependencies between each other. That's on the infra side. But on the code side, since a lot of these Lambdas, ECS tasks are just functions in the end of the day, we have a lot of libraries which all of these share, so that code is in one place, debugging is in one place, and things like that. Cool. Thank you, everyone, for being here.